In the last chapter, we learned about confidence intervals, which was the first inference method that we learned. Remember, when we're talking about statistical inference, we're talking about taking a sample and using that sample to make some kind of judgment about a population. So when we were doing confidence intervals, our goal was to get an estimate of a population parameter, like the true proportion or true mean from some overall population. The other type of inference method that we'll be learning about is called the significance test or a hypothesis test. And this has a different goal, which is to test a claim about some population parameter. So a significance test or a hypothesis test is a procedure where we're going to use observed data, which is just another way of saying a sample, to decide between two competing claims, which we call hypotheses. And these are written about the parameter, such as a proportion P or the population mean mu. Let's consider a basketball player who claims to make 80% of the free throws that he attempts. So that said, he claims that his proportion, true proportion, for the number of free throws he'll make is 80%. We think that he's exaggerating, so we're going to test the claim to see whether or not he's telling the truth. So he shoots 50 free throws and he makes 32 of them. This is our sample, which results in a p-hat of 64%. Now that's less than 80%, so this is giving some evidence that he is exaggerating and not being truthful when he said he makes 80% of his shots overall, right? But is it convincing evidence that he's lying, right? So in other words, if he really can shoot 80% of his free throws, sometimes he'll get a little more, sometimes he'll get a little less. He won't shoot 80% every time. Will this result happen just by chance, based on a typical variation in a sampling distribution? So let's look a little closer at this sample and talk about some explanations as to why he only made 64% of his shots. So the first explanation is that he's telling the truth. He actually can shoot 80% of his free throws overall, but he's not always going to make exactly 80%. Sometimes he'll make a little more, sometimes he'll make a little less. Just like if we were to flip a coin 100 times, we're not always going to get exactly 50 heads, 50 tails. So maybe this result of 64% is him just making a little less than the true proportion of 80%. The other explanation is that he's lying. He actually can't make 80% of his free throws. He makes less than that, and that's why we're seeing less than that in the sample. Now, when we look at these statistically, all right, if explanation 1 is the actual true explanation, it would be plausible for this result to happen just by chance. If explanation 2 is the true one, it would probably be unlikely for that to happen just by chance. So we've looked at these simulations before. In this dot plot, we've simulated 400 sets of 50 shots. So imagine just taking a random number from 1 to 10. If it's 1 through 8, he makes the shot. If it's 9 or 10, he misses it. We do that 50 times. We find the proportion. Each one of those is going to be a dot on this dot plot here. So simulating 50 shots for someone who actually can shoot 80% of his free throws, we see 64% down here. I'm highlighting that and everything to the left of it, so everything more extreme than 64%. So we can see that that is an unlikely result. It only happened 3 times out of 400. That's less than a 1% chance of occurring. So at this point, we have 2 explanations. Either we witnessed something that's extremely rare, extremely unlikely, and he just had extraordinarily bad luck when he went to shoot these 53 throws, or he's lying, and the reason that he's only making 64% is because in actuality, he makes less than 80% of his shots. So the fact that the probability of this occurring is so small lets us rule out that first explanation. This probably didn't happen by chance because it's an unlikely event, and instead this gives evidence that explanation 2 is correct. He actually makes less than 80% of his free throws. We've done problems like this before, but in this chapter we're going to formalize it and quantify it. So we'll get to the end of a problem and have a number which will tell us whether we have evidence for a claim or not. And these significance tests always start with hypotheses. So we'll have 2 hypotheses. The first is called the null hypothesis. It's denoted by H sub O. And we're looking for evidence against the null hypothesis. This is typically an everything's normal hypothesis or no difference hypothesis. So if he tells us he can make 80% of his free throws, our null hypothesis is just going to be we believe him. We're going to set that P equal to 80%. Now note that I said that we were seeking evidence against the null hypothesis. We're trying to disprove that null hypothesis that he can make 80% of his shots. The null hypothesis will always have an equal sign. If we're able to disprove it, we're going to be left with the other hypothesis, which is called the alternative hypothesis. The alternative hypothesis is the one that we're seeking evidence for, and it's denoted by H sub A. So if we can disprove that he makes 80% of his shots, the alternative would be that he actually makes less than that. So to recap, the null hypothesis we're looking for evidence against, this will always be an equal sign, or it'll have some kind of mathematical statement that includes a statement of equality. The alternative hypothesis is the one that we're trying to find evidence for, and this will never be an equal sign. So it can be a less than, a greater than, or a not equal to. Now, of those three options, less than, greater than, and not equal to, the first two are one-tailed hypotheses. So in other words, our null hypothesis is that he can make 80% of his free throws. If he actually can make more than that, we're not really concerned, right? We want to see specifically, is he overestimating how many of these free throws he can make? In some situations, we might want to do a two-sided test, which would be a not equal to instead of a less than, to see if the proportion is just different from some value. Let's say we were checking to see if a die was fair. We want to see, are we getting a 6 1/6 of the time, or is it happening at some proportion, all right, that indicates that this die is somehow weighted and we're not getting that 6 1 out of every 6 rolls on average. So a one-sided test will state that a parameter is greater than or less than the null hypothesis value, while a two-sided test will note that it's different from the null hypothesis, indicating that we would use a not equal to sign. So the first thing we need to figure out is how to write these hypotheses. So taking a look at example A, on its website for the 2020 census, the U.S. Census Bureau estimates that completing the census questionnaire will take 10 minutes on average. We suspect that the time it takes to complete the form may be longer than advertised. The null hypothesis is the everything is normal situation. The Census Bureau is telling us that this will take 10 minutes, so we're going to believe them and have a null hypothesis of mu equals 10. The alternative is what we would believe if that's untrue. And we get this alternative from the wording in the problem. It says we expect that this may be longer than advertised, which means the alternative is mu is greater than 10. We also note the parameter. In this case, mu is representing the true mean amount of time in minutes that it takes to complete this form. Part B, according to the National Sleep Foundation, 85% of teens are getting too little sleep on school nights. Jamila wonders whether this is true at her high school, so she takes a sample of 100 students and finds that 75 out of the 100 report getting less than the recommended amount of sleep. Now, I want to point out that there's two values here. So the first is this 85%, and the second is our sample result, 75 out of 100, which would be 75%. This 75% is a p-hat. It's the result of a sample. This 85% is about the whole population. Our parameters are always about the population. So we're never going to use a p-hat in our hypotheses, just like we're never going to use an x-bar. It's always going to be a mu for means. So we will have p equals 0.85 as our null hypothesis. And from the wording of the problem, it notes that they're getting less than the recommended amount of sleep. So the alternative would be that p is less than 0.85. These two numbers are always going to be the same. We'll always have an equal sign for the null hypothesis and some other less than, greater than, or not equal to for the alternative. All right, and we're always using population parameters mu and p, not x bar or p hat for our hypotheses. One of the things that initially seems strange about a hypothesis test is that we have a claim that we're trying to find evidence against. However, this is something that we see time and time again in society. Think of it as a criminal trial, a jury trial. We start off with an initial claim, an initial hypothesis, and that hypothesis is always the same. It's innocent until proven guilty, which means the null hypothesis is that a defendant is innocent, and then evidence is presented against that defendant. They need to provide convincing evidence where we can rule out a subject's innocence and conclude the alternative, which would be that they are guilty. That's how a significance test works. But in statistics, we quantify it and we use mathematics and data to show how strong evidence is against the null hypothesis and in support of an alternative. So let's relate this to the free throw shooter from the earlier example, who made 32 out of his 50 free throws for a percentage of 64%. This is evidence against the null hypothesis that his true proportion is actually 80%, and it's evidence in favor of the alternative, that he actually makes less than 80%. Is this evidence convincing enough for us to rule out the null hypothesis and reject it and conclude that he actually makes less than 80%? And to do this, we're going to look at a probability. How likely is it for him to make only 64% in 50 free throws? This probability is called a p-value. The p-value of a test is the probability, assuming that the null hypothesis is true, of seeing the results observed in our sample. So in our example here, we created a simulation, that dot plot, where only 3 out of the 400 dots resulted in 64% or less. That's a probability of 0.0075. That's our p-value for this problem. When it comes to interpreting this p-value, the null hypothesis being true is the condition for this probability. So assuming that the player makes 80% of his free throws in the long run, there's only a 0.0075 probability of getting a result 64% or less in a sample of 50 shots. Because that's so unlikely, that's evidence against that null hypothesis and in favor of the alternative that he makes less than 80% of his shots overall.